Today we're going to take a little look at the sum and difference rules for derivatives. And this is a very basic rule. I'm not really going to delve too deep into it, but essentially it tells you that if you're taking the derivative with respect to x of the sum or difference of two functions, so f of x plus or minus g of x over here, then that's just going to be equal to the derivative of the sum or the derivative of the difference, depending on, of course, whether or not you were initially taking the sum or the difference. So that's just going to be f prime of x plus or minus g prime of x. And obviously this is going to hold for however many functions you input here. If you're taking the sum or the difference of like 100 functions, then it's still going to be the derivative of the sum. So the way that you can think about it is that the derivative of the sum or the difference is just the sum of the derivatives or the difference of the derivatives, depending on what you initially had. And we can use this and the constant rule to make this statement over here that the derivative with respect to x of a times f of x plus or minus b times g of x is going to be equal to a times f prime of x plus or minus b times g prime of x, where a and b are just some real numbers over here. And this is a pretty interesting property. This just tells us that the derivative is a linear operator. So a linear operator, we're not really going to talk too much about that, but operator. We're not really going to talk too much about that, but it is a pretty interesting thing when you delve into linear algebra. The derivative is actually a linear operator because the sum of scaled up functions, or the derivative of the sum of scaled up functions, is just, you can kind of take those constant outs and you can kind of separate the derivative. You can just take the sum of the derivatives. Anyways, let's go ahead and actually, take these two derivatives over here. So the first one is the derivative with respect to x of 3x to the fourth plus 2 times the square root of x. Previously, we reviewed how we can solve, or we actually delved into how we can solve the derivatives of functions that have negative and fractional exponents. And the square root of x is just one of those examples. This one over here is just a direct application of the chain rule. So what we can do for this first term, the 3x to the fourth, is we can take this 4 down, and that can be our coefficient. We can multiply it by our already existing coefficient. It'll be 4 times 3, which is 12x, and then we'll have to the 4 minus 1, but 4 minus 1 is just 3, so our derivative is going to be 12x to the third. With respect to square root of x, what we can do over here, if you recall, we rewrote 2 square root of x to just being 2x to the 1/2, and then again we can go ahead and apply the power rule. I feel like I've said the chain rule multiple times when I meant to say the power rule, but if I've ever said the chain rule, just keep in mind that I was meant to say the power rule. But essentially, here we would apply the power rule, and so what we can do is we can just take this 1/2 down as our coefficient, and then we would get plus essentially 2 times 1/2, which is 2 over 2, which is just 1, and then we would get x to the negative 1/2. And then we can simplify this a little bit more. This will just be 12x to the third. X to the negative 1/2 is just 1 over the square root of x. And if you remember, if you memorize this derivative, the derivative of the square root of x is just going to be equal to 1 over 2 square root of x. And then if we were to take this 2 out over here, then the 2 and the 2 will cancel out, so we're just left with 1 over the square root of x. And so that is actually our final answer right over there. Multiple ways that you can get this, but regardless of how you do it, as long as you end up with the same answer, then it should be all right. This next one over here, we have 3 different terms. And essentially, the whole point of this is to illustrate how you can take the sum of multiple different terms or the difference of different terms, and you can always just take the derivative of each individual term. And so the derivative with respect to x of 7x squared, again, we take this 2 down, we multiply it by the 7, and we'll get 14. And then we get 2 times x to the 2 minus 1. 2 minus 1 is just positive 1, so we'll get 14x as our derivative. And then if you recall, 1 over x right over here, remember that 1 over x is just x to the negative 1. And so if we take the derivative, then we'll get essentially negative x to the negative 2. But we already have this negative sign over here, so we'll end up with positive x to the negative 2. Another way to rewrite that is just 1 over x squared. So again, if you remember, when we took the derivative previously in the previous video, we got that the derivative was negative 1 over x squared, and then if you multiply that times negative 1, it will just become positive 1 over x squared. And then finally, we have x to the 9th right over here. And so essentially, again, we just apply the power rule, so we'll get plus 9x to the 9 minus 1, which is just 8. And so that right over there illustrates how we can use the sum and difference rule in order to take the derivatives of various different functions. So it doesn't only apply to polynomial functions over here. You can always, just in general, whenever you have the sum or difference of two functions or multiple functions, then you can always just take the individual derivatives and then sum them up, or take the difference of those derivatives.